Good afternoon, everyone. Let's get started. Okay, so first of all, we set our office hours finally. This is the list. It's now also in syllabus. You can check it there. I believe all of them are in MEB, with one exception, and that's office hours with me. I already mentioned we had a serious incident with a student a year ago, and since then I'm not meeting with students in my office. So you can find my Zoom link in the syllabus at the top. And I did make a little mark on what I call Zoom etiquette, basically how I expect you to behave, which is mostly treat Zoom as if you would meet with me in person in my office, meaning don't come and go 10 times, don't just stand there with a turn off camera, not saying anything, and just a basic common sense, I would say. If you would come to my office and you ask your question, you wouldn't just linger on while I'm standing there, right? So treat the Zoom the same way, come prepared, and yeah, follow everything I just said. We try to take everyone's, time, their availability into account. That's, of course, as you can imagine, impossible. So if none of these office hours work for you, then please feel free to reach out to us to make appointments. But keep in mind that all of us on the team we have different responsibilities. So I'm teaching you, but I'm also a researcher and I lead a group. So I have my schedule divided among many things, and same with like PhD student who is doing research and is a TA and has also other responsibilities. So we can't just drop everything and accommodate meeting you. You need to give us at least a day ahead to be sure we can meet you on time. So happy to meet with you, but just be reasonable with the expectation of how fast we can arrange a meeting. Any questions about office hours? Yeah, and then I said already, we are not going to look at your code directly. We are going to try to have a conversation with you, look at how you can produce a pseudocode and wait until we actually would look into code, so not give away solutions, and be fair to everyone in the classroom. Okay, and I don't have a slide for this, but I'm sure you've seen my announcements that the first assignment is released. Remember that's something we want to submit on Gradescope. You have Autograder there, but that's not what we are going to grade. What we are going to grade is actually what we do here in the classroom. We'll talk a little bit more about that next Wednesday. I'm trying to find another room, so I might ask you to not come here, portion of you, but rather somewhere else. But I'll share more about that next Wednesday. I mean, upcoming Wednesday. Okay, these are the announcements I wanted to say. I want to move on unless there are any other questions from you. Okay, good. Right, so last time, remember, we were talking about four main components of supervised machine learning for binary classification applied to an NLP task, such as a movie review classification into positive and negative sentiment. And the first thing we learned last time, or I guess the only thing we learned last time, is how to produce input to a model. And this is one of the key things you need to remember from NLP course, is that we work with words, but what we are actually giving to our models are some numerical representations. And this is just because computers understand numbers, not exact words, right? But we also learned that we are going to have many numbers, not just a single number to represent the entire string. So we are talking about a vector of numbers. And we learned that these numbers have to capture some features of the input that the machine learning model can notice, and then notice patterns between those numbers and the label during the training, and then apply these associations later during the testing phase. So this is really, really important, right? This is how we represent input. And now the second component I mentioned is that we need some ideally probabilistic function that takes that vector and then decides which label is going to be assigned to that vector. And here we are talking about binary text classification. So for us, it is either this text is positive or negative. So today we are going to talk about that and then the other two components of a supervised machine learning for binary classification. Okay, so moving on to how to define this function, right? Like what's this going to be? And to do that, I'm going to talk a little bit about geometry of linear classifiers. So here again, you have a classification problem where we have some data points belonging to a positive class, and we have some data points belonging to a negative class. This is, imagine a visualization of your training data. And you want to restrict yourself to a class of linear models, meaning you are looking for a line that's going to separate these two blobs of labeled data point. And a general way to write a line in a 2D space is using this equation. So now I'm going to recognize that this line is the same as the dot product between this vector, which is my feature vector that contains my weights, and, this is the weight vector, and my feature vector, which contains the features of my data points, alike we have seen last time, such as bag of words. So if we don't know dot products between two vectors, so let's say I'm going to use some other words than X and W, I don't know, and then I want I, so maybe M. Okay, so if these are vectors from, let's use some abstract way of defining this, so maybe D-dimensional. Then the dot product between them is going to be the sum of their basically element-wise product. So it's a sum from I equals 1 to D between yi times mi. And there are different ways people write this. So very often you will just see written it as I've written it here, just product of these two vectors. But some notation you might see is this one. Let me think whether there is any other common way. Do you know any other way of writing dot products you've seen before? Yeah, so maybe sometimes you'll see something like this. Okay. So what I want to mention here is that this weight vector, and ignore for a moment this dummy variable 1 and the bias term W0. If we just focus on these coordinates in this 2D space, every point here has x1 and x2 coordinate, right? So that's how they live in the space. And focus for now just on the weights W1 and W2. If you produce a vector from W1 and W2, like here, this vector is basically a normal vector to this line. And it is pointing towards the data points that are labeled with positive sentiment class. This is how we define the problem. So we are looking for a line, the weight vector that makes up the line as well. The normal to the line is going to be defined as a vector that points to the positive class. And a way to think about this geometrically is that each one of these data points has x1 and x2. And if you have this normal that defines this line, then, and it should point to the class belonging to positive sentiment, then each one of these x1 and x2s kind of tells you about what's the contribution then each weight represents the contribution of the corresponding feature to the model. In other words, if my x1 and x2 are very aligned with this normal vector w1, w2, then I know that that data point is more in the direction of the positive class than something that's completely opposite of that normal vector. And the dot product kind of gives you this notion of being aligned with that normal vector. Dot product between x1, x2, and w1, w2, if it's very high, that means that your data point is in the direction of the positive class. And if your dot product between weight vector and feature vector is really small, that means that you are in an exact opposite direction of the normal, meaning you are pointing in the exact opposite direction than the direction of the positive sentiment class or whatever else binary problem you have. So yeah, things to remember here with a linear classifier is that the normal to the line is basically that weight vector. It lives in the same size of vector space as your data points if you ignore the bias term and the dummy variable one. It is pointing, we have collectively agreed, this is going to be where the positive data points are. So it's a direction of positive data points. So our coordinates of each data point together with that weight vector kind of tells us, oh, is this data point in the direction of positive class or not? And we are going to use that notion quite a lot today, being in the direction of a positive class determined by the dot product between the weight and feature vector, which should be positive if the example lives in a space where the positive data points are. Okay, let me give you one just technicality covered here. I keep saying ignore these dummy variables and bias terms. So basically, to be able to write the dot product between feature and weight vector, being the line, being basically our classifier, we needed to introduce this dummy variable 1, such that 1 times W0 equals W0, right? So usually what we do is we fold this dummy variable 1 at the beginning of our feature vector, such that when we define our weight vector being W0 all the way to other weights, then we can do dot product between two of these because they are equally dimensional. They're of equal size. So this is something we do a lot of time, and this enables me that then I don't need to keep writing this bias term. Sometimes you will see instead of something like this, someone might define the classifier as W0 times WD and f of x, where these are R in RD minus 1, not in RD. And this is just a little bit less elegant way of writing things. So very often we will just fold into the bias term, and then especially when you start programming these things in PyTorch, you don't want to have any additional sums or anything. You just want to work with vectors and matrices, and later on tensors, which are higher dimensional generalization of matrices. So this is just a technicality. I will in this course never mention bias term. I just imagine we are all on the same page, that it's folded into a vector. Okay, so now I have my weights. I have my feature vector. Imagine we have a bag of words. And imagine I say, well, I'm going to embrace this geometry that I just explained to you and decide that as soon as the weight vector and dot product between a weight vector and a feature vector is larger than 0, meaning that the data point is in the direction of the normal to the line, meaning where we said positive data points live, I'm going to say that's a positive example. So now I'm also introducing a notation where I say I equals 1 means that the label is positive and I equals 0 means it's negative. So that's my way of defining a classifier, a classifying function. Do you remember something else I wanted that's missing here? Yes, please. Exactly. So here, what is the range of a dot product between numbers? How small and how large can it be? Okay, can you raise a hand if you know the answer? Yeah. Exactly, it's unbounded. So negative to negative to positive infinity. So quite a range. And our probabilities should be in which range? 0 and 1. Great. So we are more confident about that one. And so this is definitely not a probabilistic notion. I don't get anything here. I made a decision, oh, this is going to be a positive class, but all I have is this dot product, which can be really, really high, and it doesn't tell me how likely then this example is to be a positive sentiment class example. Although now when I said this, you might be like, well, if the dot product is really high, shouldn't we then say probability is very likely it's a positive sentiment example, and you would be exactly right, and this is the notion we are going to now formalize with math. Okay, so to introduce that notion of probability, we are going to introduce a mathematical object here as a tool from our toolbox to define a probabilistic version of classifier I have defined before. So here I'm just defining what a sigmoid function is. I'm not yet giving you a probabilistic version of that classifier. This is a sigmoid function. It is defined through this equation. And if you plot it, you will get a line that looks like this, or I should say a curve. And what you can notice is that around 0, it is almost linear, right? But then if the values, input values z's, are very high, then we are going to get sigmoid of 1. And if the z input values are really small, then we are going to get sigmoid value of 0. Now that I said that, do you have an idea how would you change what I had before to introduce the probabilistic classifier using the sigma? Let me wait and see whether there's anyone else. Okay. Yeah.
For the output, it's the sigmoid function. Use output.
Exactly. So here the let me just clarify what do you mean by output.
Yeah. Interesting.
Don't forget about the what you get. Yeah. Sorry. Let's forward this again. So what is the input to this point? Exactly. Okay, great. They're on the same page. So basically, I said this dot product gives us some notion of how aligned this feature vector is with the weight vector, right? And more they are pointing to the same direction, these two vectors, more likely that this example is going to be a positive sentiment example. So now I have told you sigmoid function, all it does, it takes some values, and if these values are really large, the output of the sigmoid is going to be 1. So basically, if the dot product between a feature and the weight vector is really high, and these two vectors are pointing to similar directions, then you're going to get a sigmoid which is very close to 1, which is exactly what you wanted. And exactly opposite, if the dot product is really small, meaning that the data point is in a completely different direction than the direction where the positive data points live, then you give that dot product to the sigmoid, and it's going to be very small, and very sigmoid of the very small number is going to be squished to 0, which gives us a notion of probability of 0. So that's the idea. Very simple tweak to achieve that probabilistic notion with this classifier, which I'm going to come back to this. So here is everything together. We define the sigmoid function, and now value z is basically this dot product between the weight and a feature vector. And we just give it as an input to a sigmoid function, and we get value between 0 and 1. Now, because we have only two possible classes, if this is how we define the probability of being positive, then the probability of being negative is just 1 minus probability of being positive, because we have just two possible outcomes in this probabilistic setup. And this is basically now, you know how I said, first we define a feature vector. And after we define a feature vector, we need to define some probabilistic classification function, right? And this is exactly it. We have just defined it, right? What's missing here? Like, what do you don't know here? What's undefined? Yes.
When the x-axis is 0, like what's the quantify?
If your entire vector, so just keep in mind we are talking about vectors here, so there isn't a single number. If your f of x is a zero vector, I should say, so now it's a bit potentially confusing because the input to the sigma is dot product, right? So if the dot product is 0, the sigma will be 0.5. Yeah, and we are going to use that in a second as well. But that's an element that's missing. How does this decision of thresholding changes then? Here, when you look at all the symbols, for example, f of x, we can define as a bag of words, right? So we know kind of what's that, and we have label data, so we know whether the example is a part of the true or the positive sentiment or negative sentiment. But something here is quite underspecified, like what would I need to find for this model to actually work? Yes, weight vector, right? Like right now, remember when I showed you last time very different lines with they were just ax plus b, so very simple problem. And then I was changing a and b, and you were getting different lines, right? And I said the goal of machine learning, supervised machine learning, is to find proper weights on parameters. Right now, I have defined a family of potential logistic regressions, right? There is so many of them because we can change these weight values to be many different values. So the crux now is to find what are the right weights values such that when we use these equations with those weight values, work whatever new movie review we get in the future. So that's the goal. But I do want to come back to the point. Sorry, I don't know your name, Tasni, mentioned. So here previously I said the dot product needs to be positive for us to determine that this example is going to be a positive sentiment example. So now here, if we use our new formula, which is the sigmoid of the dot product, then we just set, well, if my dot product is higher of 0, then what's the value of sigmoid is going to be? And basically, if you check, the sigmoid of 0 is 0.5. So that means, because sigmoid is also monotonic, that your probability needs to be higher than 0.5 for you to say that this example is going to be positive sentiment example. And basically, this is your final classifier. So you say it's a positive example if the probability is higher than 0.5, where probability is the sigmoid of the dot product between feature and weight vector. You might have noticed that before I use greater or equal to, here I am strictly greater. This is yet another hyperparameter that we talked about before. You can decide whether 0 is going to be positive or negative for you. There is no rule for that. Okay, and one side note I want to mention is that so I showed you this part for, like, I defined sigmoid like this. But if you do a little bit of arithmetic, you would also get that this equals to this. So sometimes you will see sigmoid defined like that, and don't be stressed and think, oh no, Anna showed us the wrong equation. These are the same thing with just slightly different calculations, okay? And sigmoid of z is equals 1 minus sigmoid of minus z. This is a property of a sigmoid you might see somewhere that might be useful. Okay, so now just to go over what we know so far. We know that I have given you a movie review. You need to classify it as positive or negative. First thing you learn, I need to produce a feature vector, and I have few options right now, bag of words, bag of n-grams, DF, IDF. Later, you'll have even more options. And then once you have that feature vector, you need to define some family of potential models for classifying that feature vector into a positive or negative class. Here, we restricted ourselves to logistic regression, which is basically giving us probability of an example being positive, being the sigmoid function of the dot product between feature and weight vector. And with that, we have infinitely many logistic regressions because we can set these values W0s to WD minus 1 to be, each one of them has infinite options for what they could be. So now the goal is to find the right ones, the ones that are going to separate training data well and also generalize to unseen instances. And that's what we are going to talk about next. But before that, are there any questions? Yes.
For the class in general, are there any laptop requirements or can we use Google Colab? Is there any recommended IDE or software for the projects?
Maybe for these logistic classes, questions, let's stop later because I'm not sure everyone is interested in any questions. So let's stop after the lecture. Yeah. Yes.
So the actual separation of the training data is a separate line from what we're using the weight vector for, right? But we're using that line in reference of the zero.
Not sure I quite get your question. So you have your weights and weights define the line, right? So let me see, let me find the white, like here it is. So here is some set of lines, right? That are defined through specific weight values. And here you are, the way you would plot this line is by setting different x1s and x2s, right? Yeah, to kind of plot it. So it's a relationship. If you think about this being a function, then it would be a function of x1 and x2, where your weights are set. So you have to choose them somehow before to define that function, right? And then you just change x1 and x2. Does this answer your question? Yeah. Yes.
Is there any connection between that line and the 0.5 threshold?
Right. So there is a connection between dot product between my points and my weights. I say need to be the dot product needs to be positive because that means that if I had this data point here, dot product between the vector to that data point and my weight vector is going to be positive. And I said my weights are going to be determining where the positive examples live in. So now if you had an example like one here, and if you had vector pointing to that example, if you were to do dot product between that vector and this vector W1, W2, you would get negative value. And this is why we threshold with 0. And now how come 0.5 comes about? This is just because now we have introduced the sigmoid, and sigmoid, when the dot product is larger than 0, is going to be sigmoid of all such numbers is going to be higher than 0.5. And this is why we threshold with 0.5. Yeah. Yep.
Just to clarify, this decision of having this threshold for 0.5 for our sigmoid versus greater than or equal to, this is a hyperparameter that we can tune for performance?
In this setup, no, because again, let me maybe write it down here. So again, W and f of x. So this is my weight vector, and this is my feature vector, which kind of shows that here we have another way of writing this, and also sometimes write, depending on how you define them. So I have this dot product, and if there are these two vectors geometrically are pointing in the same direction, the dot product is going to be larger than 0, right? So this is not like a hyperparameter. This comes from our intuition of what should happen with these vectors, right? And now when I apply the sigmoid to this thing, if this is larger than 0, these are my inputs to the sigmoid. So you can basically equate dot product with z here. So right here, z is my dot product. And I say this dot product needs to be larger than 0. And then you just check what's going to happen with the sigmoid. You see that these values for these numbers are going to be 0.5 or higher. And this is why there is a 0.5 over here.
I'm just wondering what happens in a possible scenario of the sigmoid equaling 0.5.
Oh, I see. Yeah, so whether you're going to have strict inequality here or not, that's a hyperparameter,
Yeah,
right?
that's what I was.
Okay, sorry, my bad then. I was thinking you're asking whether here we can choose instead of 0, like 0.1 or
No.
0.2. Yeah.
Right.
Okay, then we are on the same page, yeah. Okay, so now, as I kind of poked before, we just set how we are going to model this problem, but we didn't actually find the right classifier. So right now we have many options at our disposal, and our goal is to find weights that are going to separate training examples well, and then when we apply to unseen instances, it's going to work well. So we are going to now see how we are going to do that. And for that, I'm going to use the whiteboard. And we are going to write some math. Okay, so if you have taken machine learning, this is going to be quite basics, but I do want to go over this carefully because it's important that those who didn't hear about this before should know about it. Okay, so we are going to, again, we are dealing with supervised machine learning. So that means we have labeled data, right? So we have a data set, D trained, which is a set of examples where we have input xi and label ii for each one of those. I'm going to use this notation to denote there is D such examples in this data set. Okay, so again, we will have a logistic regression. Our goal is to find weights, appropriate weights. And the way we can use this data to find appropriate weights is to define an optimization problem that says, well, let's maximize what we want. We want to find the weights W such that the probability of seeing example label Y1 with input X1 and giving those weights is really high. And we want to do that for every single example in this data set, right? So we want to see example label ID if we give it example, input example XD and those chosen weights, right? So basically here we have a joint probability of these conditional events. And this should be intuitive to you, right? Like if my label data, if some human annotator said each one of these labels should occur with the corresponding example, you should have told me there is a mistake here. This is one. So if I give it first example and some human had said, well, then you should have label I1 here, then I want the probability of that label occurring given that example to be high, and then for each one. And this is called maximizing likelihood. Okay, so that should be intuitive. I hope it is. And now, this is where some of the assumptions we make in machine learning come into play. So those who have taken machine learning, what's the main assumption we make? Who has taken machine learning? Who has taken deep learning? All right, I see at least collectively 10 hands. So some assumption Don't worry, nothing's gonna happen if you say, I want to tell your instructors, you know.
The training data is correct.
That its training data is correct. Yes, that's one assumption. We believe that these IIs are correct, and therefore we want to maximize seeing them given the input. Okay, you haven't, IID, right, assumption. So IID means that these examples are independent and equally distributed. And it's a main assumption we make in machine learning, which is often wrong, but it makes us model many things we wouldn't otherwise be able to model. So we know if examples are IID, then the probability of two independent events, right? I can write it as a product of their probabilities. So here, yes, I have joint probability of seeing these events, but I assume that whether this label is going to occur with this example is completely independent of what the label of this example is. And once I assume that, and once I assume that underlying probability distribution is the same for each example, then I can use my independence rule, and I can write this as a product of probabilities. So now I'm just using this, I mean, everything here, to rewrite this optimization as the product from I to D between these probability values. Okay, so here we use IID. Okay, now you might have not taken any numerical optimization classes, but when you are dealing with numbers, it's easier to optimize sums than products. This is just something that you know empirically, that products can basically explode and be finicky to optimize for. So we like sums more than products. And luckily for us, we can just apply logarithm to all of this to basically get from the product sum. Because remember that the logarithm of a product is a sum of their individual logarithms. What's important here is that logarithm is a monotonic function, so your maximization problem doesn't get weird. Basically, if you had, I'll write here 1 and 2, I will say that log is monotonic. Meaning, if I had z1 being larger than z2, then the logarithm of z1 is going to be larger than the logarithm of z2. So when I'm looking for my weights that maximize all of this, it doesn't matter that I now introduce logarithm, because the same weights that maximize these probabilities are also going to maximize their log probabilities. So nothing has changed in terms of the objective function. So now I can write. So here I use that logarithm of A times B equals blah, blah, blah. And I use that log is monotonic. And now this maximization problem becomes maximizing sum of log probabilities. Okay, now again, we are doing some machine learning here, but we are using tools for numerical optimization for numerical analysis. And those people, they didn't have specifically machine learning in mind, they rather were interested, how can we find the minimum of functions? And they have caused all their problems as minimization problems. And now we are dealing with maximization, which is It's just like you want to use an existing implementation. It's designed to be for minimizing, and you'll have maximization, which is like, what to do. And the easy thing you can do is just basically multiply all of this with -1, and then your maximization problem becomes minimization problem. So you're minimizing sum of negative log probabilities. Here, so maybe I'll write it here. Basically, if you have f of z1 is larger than f of z2, then you know that minus f of z1 is smaller than f of z2. Or in other words, if you find some weights that were maximizing this problem. So here some weights were, you get larger log probabilities with those weights. Then when you multiply everything with -1, you know that those same weights are going to be minimizing the minus f function. So everything is okay. And here we are just going to define this bit as our loss. So this is an important concept in machine learning. We often are introduced notion of a loss, and we are trying to minimize loss. And because here we have this negative log likelihoods, this problem will often be called the negative log likelihood optimization problem, which is exactly what you can see there in the overview. So let's go further with slides. Is anything in this calculation unclear? Should be in slides. I will take a photo anyway. To prepare that one. Oh no, the phone is not working. Okay. Okay, I don't know how you can use it. Okay, so this is pretty standard. So even if right now maybe it doesn't immediately click, you will find about 300 million resources on this, including these slides and recording. So everything is also written here. So now just remember why we have derived with this objective, this optimization problem. We derived it to find good weight for our logistic regression. So although this might be a little bit more, it's not a little bit, like it's a more general framework for how to optimize different models in machine learning. Today, we are applying it to logistic regression. So we have specific definitions for what a probability is, right? So now we are going to go back to those definitions, which are that the probability of seeing a positive class for the input is the sigmoid of the dot product, and probability of seeing negative class is 1 minus probability of seeing the positive class. So here, what you can do is each of your training examples is labeled in your training data. So you know which probability you should be optimizing for. So remember that this is probability of seeing the true, we say gold or ground truth label for that input example. So if you know, and you know because you have labeled data, that your example is labeled as positive, then you would use equation for positive probability here, and otherwise you would use the 1 minus positive probability. So you are always using the right probability here if you would to train logistic regression with negative log likelihood. And this is important. This is something you are going to implement in the assignment. So just pay attention to this detail that here, this is not a probability of whatever label. It's a probability of the true label for that input, which you have access to in your training data. So the probability equation you're using depends on what the true label is. Okay. how do we feel about like a side note, not super important right now discussion? Should we leave it for some other day, or you feel like you have bandwidth? I want to talk about why specifically for logistic regression, negative log likelihood and cross entropy objectives are the same objectives. Are you feeling a little bit tired from this math so far? There is more math to come, I should say. I don't hear like super strict no, so this can be also a lesson in learning how to say no, no more math. So let me just quickly go over this. This is basically what we know so far. We have defined equations for the probability of seeing positive and negative class. And I have defined what our objective is going to be for finding weights. It's going to be minimizing negative log likelihood. And there is this way you can write this negative log likelihood specifically for logistic regression here. If we define two possible labels, 0 and 1 being positive and 0 being negative class, then trust me when I say to you that negative log probability is exactly the same as this more extended equation that you see here. And basically, now do mental gymnastics with me. If a label is positive, it means that I equals to 1, right? So in that case, you will have minus 1 times log probability of seeing 1 for that input example, minus 1 minus 1, which is 0. So this term gets canceled out. And what you're left with is minus log probability of seeing positive class for a positive example, which is exactly what we want to minimize, right? And if you have a negative class, then we have I being 0. So we would cancel out this term here because this is 0. And what we would be left with is minus 1 minus 0. So minus 1 times log probability of 1 minus probability of seeing positive example, which is log probability of seeing a negative example, right? Which is exactly what we would minimize here. So these are equivalent ways of writing the exact same thing in the case of binary logistic regression, okay? And this form over here can be connected to something called cross entropy. So from information theory, somewhere you might have heard, you know, if you have taken something like signal processing, you have certainly heard about cross entropy. And basically this equation here is cross entropy function. So what this means is that negative log likelihood with logistic regression for binary classification is the same thing as cross entropy. And you will see later when we start implementing these things with PyTorch that you will have both function negative log likelihood and cross entropy that will be used slightly differently, but they would give you the same output if you use them correctly for binary logistic regression. So if someone tells you, and this is, I think, a common confusion point, I taught you negative log likelihood, and someone is like, oh, shouldn't you learn like cross entropy? You can say, well, they are the same thing. So we just call them slightly different and introduce them in slightly different way. I like this way maybe because I do like these calculations. They are, to me, very intuitive, where with cross entropy, you need to understand what cross entropy is from information theory. Okay, so that's my little digression. Now, we came to a point where we have an objective function that we want to optimize to learn our appropriate weights. So I set the optimization objective for us. I said we are looking for weights that are going to minimize negative log probabilities, right? So now we have a goal in mind, but we lack an algorithm to find those weights, right? So we don't know, we know we need to find weights that minimize this, but we are like, how do we know which weights are going to minimize that? And this is exactly what we are going to then cover next. Okay, it's been a little bit heavy on math today. Would you appreciate a little like 2, 3, 5 minutes break now? Yeah, okay, someone learned the lesson, great. Okay, let's take a 5 minutes break and then we are covered the rest.
Yes.
Yeah, so that's why Yeah. That's right. Yeah. No, this is the space. Yeah, that's what I. Yeah.
Okay, let's get further. So remember. This one. The last one's gonna be fine. Okay, if you don't see, just raise your hand. I have options. Yeah. Okay, so right, so we have this objective function, and now we are looking for ways how we can find these weights W. And this is compactly with written at the top. The goal is to find this W star that are minimizing the loss, where loss is for us negative moduli. And here we are going to use an algorithm called gradient descent, and I'm going to give you an intuition of why does this algorithm exist? Why was it defined the way it was? So for that, imagine we work in space we'll never work with one-dimensional space. So we have our weights, what we are trying to find, being on an x-axis, and then on y-axis we have loss of W. Do you see this? Okay. Okay, let me know if something's not visible. And imagine your loss function looks something like this. So this is the loss function, and you're trying to find minimum of this function, which would be here, right? Okay, so now the question is, how do you find it, right? And here, the way the gradient descent is going to work, we are going to choose W pretty much random. Imagine I pick a random W and I hit this one. So this is my W1. And now the question is, if I have started here the loss definitely is at its minimum, right? How can I get to this point? How can I from here go basically to the right and get to the W minimum? The way we are going to do this is to use the derivative of this loss function in this data point here. So here the derivative loss of, or I don't know which notation you like, so I'm going to write both of them. Basically, if you remember derivatives, we are looking at the slope of the tangent line on the curve of this loss function, right? So that's what derivative is. If you forgot, just a quick reminder that geometrical interpretation of the derivative that you learned, I hope, in analysis 1, if not earlier, is the slope of the tangent line, which is that line that just touches the curve in this point you have chosen here. So here should say W1. Okay. So that's what you get with the derivative. And basically, if you take the negative derivative, it's going to consider what the slope is like. If it's negative like here, taking negative derivative is basically pushing you to move to the right. And here where the derivative, where the slope of the tangent is positive, taking negative derivative would force you to move to the left. So you use this geometric intuition to then say, well, this is great because that's exactly how I want my, weights, how I iteratively want to change them. You just need to determine how much you're going to move to the left or right, and that's going to be determined by something called learning rate, which is a hyperparameter you define. Usually it's denoted by lambda or alpha. The values you also see are 0.1 or 0.001. It's a hyperparameter, so no one can tell you magical number beforehand, but just to kind of give you a range, you won't see learning rates of size 10 or 100, that's uncommon. And basically what the learning rate decides is I'm going to take the negative derivative, meaning I'm going to move in the direction defined by this tangent, but if I'm going to move downwards. And how much I'm going to be moving depends on the learning rate. So if I move like this much, I'm going to move somewhere here, and that might be my W2. And it's important to select learning rate carefully. It's the most important hyperparameter, because if you pick a huge learning rate, what's going to effectively happen is you are going to go on the other side. And that's not good, because now you're going to start oscillating, and we don't want that. We want to go like slowly downwards and then hit the derivative of 0, which means that it's plateaued. This is where the minimum is in the case of convex functions like this one. If you take a tiny learning rate, then everything becomes small. You're basically making these tiny steps, and you're making your wasting computation by needing many, many more steps of iteration. So your learning rate can't be too small, but it can't be too huge. And this is why it's one of the most important hyperparameters, because it determines the entire optimization process, and you can make wrong decisions, for example. Okay, so I think that's the everything I wanted to say. So remember the geometric notion of the derivative that you learned way back, another tool in your math toolbox. You know, it's a slope of the tangent in that point. And then the negative derivative gives you the direction which is opposite to the slope, which means that if you are like here, you're going to move to the right. If you are on a positive slope, you're going to move to the left. And now, how this is implemented. Let's see the algorithm here. So first of all, you are going to randomly set your weights to some numbers. For now, you are going to make some not super important decisions. Maybe it's going to be just all zeros or all uniform, like sample from uniform distribution from a given range. Later, when we start to go into deep learning, these decisions are going to be quite important, and we are going to learn different, more small, clever ways of doing initialization. That's how this is called. We are going to choose a learning rate, which is our hyperparameter, something like 0.1. And then we are going to iterate. So here we are using a notion of epoch. Actually, right here, epoch versus iteration. And people are going to mix these words. I will tell you how I typically use them, but even I slip and say different things. So when you are iterating over the entire data, such as here, so here in single epoch, you are going over entirety of your training data. This is when I typically use epoch, when I go over the entire training data, and I reserve step or iteration when I use a single data point. That's a common distinction between epoch or steps and iterations, but you will see people mixing both, so it's not terribly, important, I would say. So we might go over the data multiple times, and it's important to shuffle the training data because sometimes if the model sees the data in exact same order, it can start to use some information about that, which is not good. Remember here we have assumed they are IID, that they are independent of each other. So we don't want the model to think, oh, these data points are in any way related to each other. Later, not yet, not for your assignment, you can tweak the learning rate through epochs. That's very common these days to start with a little bit higher epoch, and then we have something called warm-up stage and all the not complicated, but more intricate ways of dealing with the learning rate. Here, you can just assume it's fixed throughout the training. And now, here is, I'm saying gradient instead of the derivative, because remember that your input is an actual vector, right? It's not a single variable. So we need the generalization of the derivative to gradients. I'll write it here. So for us, we have f of x being our feature vector. We are classifying it into this probability, right? So something which is just R. So it's a real function. We are looking just for real number out of a vector. So when we have gradient of f of x, no, sorry, that's wrong. Gradient of a loss, right? So I'm kind of generalizing notion of a derivative of a loss to what happens with what is derivative when my input is not just one dimensional, but it's rather high dimensional. So here we have a gradient with respect to the weights, which is a vector of my loss function, which is a function of that, which is just a vector where we have partial derivative. So partial derivative with respect to the first weight, or I should have here 0 of the loss, all the way to, again, the partial derivative of the loss with respect to the last weight, which is d minus 1. And that's going to be a vector of the size rd, okay, instead of just one number here. Okay, so I compute the gradient of my loss functions with respect to dw, and then I do this update. So this update is basically doing that moving here with a certain like value, which is determined by this gradient or in a 1D space with respect to the derivative. So I take my weights and I subtract from them value learning rate times the gradient. I'm subtract because I said I am taking the negative derivative or the negative gradient. So this minus comes from the fact that I'm moving downwards. Otherwise, if I had plus, I would move upwards, which is not what we want. We would end up at a minimum. So changing weights to be just slightly smaller by the value of learning rate times the gradient is how you move from W1 to W2 here. It's basically mathematically writing that operation. And again, notice why it's like how this now everything matches. My weights are the dimensional vector, and I'm subtracting again vector of the same size. So it works, right? Like if I had the derivative, like I wouldn't be able to subtract a single number from a vector. Okay, so this is again important, something we're going to implement in the first assignment. This is called stochastic gradient descent because you are basically changing the weights with every single example. Later on, we are going to learn more clever ways of doing this because this is maybe too aggressive. We are changing with every example. How about we take what we would say a small set or a batch of examples, calculate the gradient of each one, average it, and then change with the average gradient. This way we don't, if there is some outlier, it won't destroy everything. Okay, is this clear? Okay, I see some nods, some like maybe not so convinced faces, but I think once you start implementing this is going to become clearer. Now, again, how do we use this for logistic regression? What is missing here? What do you know? What don't you know? Yeah.
So we want the loss function and then the loss regression loss function, which is
So we know what the loss is, right? We have the log probabilities, we have defined the probabilities, but what if I would tell you, drop everything now, implement this, what didn't I tell you? And you would be confused how to implement.
how to take the derivative of a function.
Yeah, exactly. I didn't tell you how to do this gradient calculation or derivative. So that's what's missing, and that's what we are gonna go over next with some more math. Is it helpful if I write on the whiteboard, or should I just go over slides? Whiteboard helps. Okay, it definitely slows me down, which I think it's appreciated. Let me just take. Okay. Oh. Another one. I'm so excited. I hate cleaning them. Okay, so let's go over this. I will go over how we calculate the derivative in the case when the true label is positive, and I will show you then like the equation of what happens with the gradient if the, sorry, I said loss is positive, I meant the label is positive. And then I'll show you what happens if true label is negative, but I won't derive it, and I will leave that for you if you want to do it as an exercise for yourself. Okay, let's go over this. So we want to know the derivative of with respect to the weights of the negative log probability of yi given xi w. And I'm going to write this as derivatives, all the reality unit gradients, just because Actually, I don't know what I wanted to say here. Never mind, I confused myself. Let's work on this. So we have the this probability in a case where we have positive label, right? So assume xi is labeled by some human annotator as a positive sentiment example. Then I know that probability is this formula here, the sigmoid of the dot product, which then equals to here. I'm gonna write it down. Ugh. I had enough of math for today too, seems like. Negative log probability of this fraction, 1 plus e to the dot prob w t f of x. Okay, and now we are going to just basically use a bunch of rules about derivatives that we know from, again, I believe analysis 1. So the first one is going to be here, not even a derivative. We know that this logarithm equals to, so we know that the minus log of x equals to the logarithm of 1 over x, right? So we are going to just use that. Which means that this denominator is gonna come out. Okay. And now we're going to use a bunch of rules from that we know from derivatives. So the first one is gonna be chain rules, right? Like here we have a chain of a composition of function of logarithm, and then this sum, and then the exponential function over here. So we are going to basically use, I will write it one here, chain rule, which is that if we have I equals f g of x, then its derivative is f derivative of f in gx time derivative of g in x. So that's the first thing we are gonna use. So here and then the second thing is that what's the derivative of the logarithm? I'm assuming this is a natural logarithm. So derivative of natural logarithm is going to be 1 over x. So first we take whatever is inside the algorithm, the logarithm. So it's going to be again 1 over 1 plus minus wt f of x, right? So it's clear how we came here. Okay, and then here we have a sum, which is another, like it's composed of two functions. You can think of this one being f of x. It's a constant function. It doesn't depend on w, so its derivative with respect to w is going to be what? 0, right? And then we know also that if we had the derivative of a sum is a sum of derivatives, right? So this is basically what I'm doing here. All right, I don't know where I wrote it, but it's basically of f of x plus g of x equals to derivative of f of x plus derivative of g of x. And we also use that the derivative of some constant function c is 0, where c is just some real value. So we have used so far 1, 2, 3, 4. We said that here this is gonna be 0. So now I'm left with the derivative of this thing. I know that the derivative of exponential function is again exponential function. So I'm gonna write it. But it's actually composition of exponential function with this function. And we are taking the derivative with respect to w. So here we have basically a function of w, which is just identity function times some constant minus f of x. So what's left is then what? Minus f of x, perfect. Okay, so let me just write all of the things we use such that we have them. 5 is d of f of x, with respect to x is e of x. And we had that the derivative of some function c times f of x. Sorry, this was c times x equals c. Okay, bunch of stuff. Do you recognize something here? You can check the slide for inspiration. Okay, I'm gonna give a little hint. Does this look familiar?
Yeah, that's the
Probability.
Okay, probability of
probability that y is 0.
0, right? So this here is probability that yi equals 0, given xi and weights. And then we have again times f of minus x, and we have minus somewhere, right?
Yeah, it's negative.
Yeah, negative, this one, right?
Yeah,
yeah.
it's negative f of x.
Yeah.
Multiplied by that probability.
Yeah, so I just put it here because it's mathematically fine and I don't have space here. So this is good, except that this is wrong here. Minus crept into f of x. This is good, except that you can finish here, but because you are going to likely, when you implement, you'll get the probability of being positive. So you can, instead of them doing 1 minus blah, you can immediately consider that. So this probability here is 1 minus probability of being positive class. And now, again, a little bit mental gymnastics with me. 1 minus something, if I have minus in front, it's going to become x, that thing's minus 1, right? So I'm going to write it basically. Let's keep this minus together. So maybe later you remember that this color together means probability of yi equals 1, xi w minus 1 times f of x. And that's it. That's what we wanted to calculate. In case when you know x, your input example is labeled with a positive sentiment class. If your example was an example with negative sentiment class, then you would use this equation here. So that's important. Basically, and the only thing that happened in your gradient descent algorithm right now is that you would use different equation for your gradient based on whether your input example is labeled as positive or if it's labeled as negative. Give me, we have 1 more minute, so let me just finish by saying that with this, with only a couple lectures, you have learned how to create a sentiment classifier using some basic machine learning. You have learned that you can represent your movie review with bag of words or TF-IDF. You then learn, oh, I can define logistic regression, but then you are like, it's cool, but I don't have weights. There are many weights I can choose. So I need to have some gut, right, to choose right weights. And that was our optimization problem, which is minimizing negative log likelihood, which is for logistic regression, same as minimizing loss entropy. And then now finally, you have, this is your guide, but this is a thing, this stochastic gradient descent with these gradient updates are a way to change weights such that you minimize this thing. So now you have all the pieces of puzzle to actually train your logistic regression. And once it's trained, you can go into the testing phase where you apply you no longer care about the optimization because that's done with training. Everything that's left in the testing phase is your feature representation and your now logistic classifier with the weights you have found through the optimization, right? And I didn't get to talk about it. It is important for your assignments. So how do we evaluate this thing? In assignment, we use accuracy, which is basically in your test data or development data, you again have labels of what's sentiment positive, what's sentiment negative, and then you can use your classifier to make decision, but you can check how many times your decision agrees with the human one. And then F1 score is a more robust notion of that, which is not super important. So for now, just maybe check what's accuracy for your assignment and let us know if you have any questions. Right, thank you.